Appreciate that. The title of the talk is Put a Socket in It, Understanding and Attacking Android Sockets. So, my name is Jake Valletta. I'm a senior consultant at Mandiant. I work out of the San Francisco office, previously worked in the New York office. I mostly focus on red team activities, like Chris and Evan who spoke earlier, but I also focus a lot of my time on mobile research. I, for some reason, really like mobile security. Looks like it's a little bit cut off. If it's a problem, just raise your hand. I can explain things. So just a quick agenda for the talk today. I'm going to start and talk about sockets. Has anybody here done socket programming in any sort of language? Okay, so a few people. This is not going to be a talk talking about socket programming in any language. It'll have some basic information, but you can take entire classes on socket programming. What I want to do is just show you what they are, what they're used for, give you some of the basics, and then you can do the rest of the research. There's great resources online that are probably better than what I have here. Next, I'm going to talk about IPC, inter-process communication on Android, and how sockets kind of fit into that picture. With these two out of the way, these are mostly technical sections. We'll talk about how you can actually attack sockets on the Android operating system. And there should be plenty of time for questions at the end if anybody has any. So let's start by answering, what is a socket? Well, sockets are everywhere. Every connection you make on the internet is a socket. There's a lot of connections that happen locally. There's sockets everywhere. At a very basic level, a socket is a way to perform IPC. Like I said, this is both across a network or just locally between processes or between sections of a computer. Why do we care, though? Well, there's many reasons why we should care. One, sockets are used extensively by the Android operating system, not so much by applications, but by the operating system itself to do critical operations. If anyone's seen me talk in the past, I really like to pick on the OEMs. These are Samsung, LG, whatever. These guys just don't seem to do things correctly, and this is the reason why phones are rooted all the time. It's because of the OEMs. Every once in a while, there'll be a really cool Google bug, and like stage fright, that's awesome. But a lot of times, these phones are rooted because of the OEMs. So I'll be picking on them. I have just a few examples here that were related to sockets. I have other ones that I unfortunately can't put on here because they're done on various assessments that I've done through work, and I don't want to lose my job. But I can talk a little bit about them, what we found, some high-level things. Now, the first one I have on the list here is from 2011. Okay, it's a little bit old, but in 2011, the VALD process, the volume daemon on Android, listened to what are called AF netlink sockets. We're going to talk about these in a lot more detail. But it was listening for connections, and basically it was a way for the kernel to tell a user space process running as root that a drive had been plugged in. So for example, you plug an SD card into your phone, the kernel tells VALD that a drive has been mounted, here's where it should mount it, blah, blah, blah. Unfortunately, VALD didn't validate that the kernel was talking to it on this socket, and anyone could talk to the VALD process, which meant that you could simulate this and basically mount an arbitrary drive as whatever parameters you'd like, and root a phone that way. This was called Gingerbreak, if anyone remembers. Weak Sauce, this came out a couple years ago. This was a Unix-based socket, again we'll talk about these, that was able to root a variety of HTC phones. This was a socket listening that performed ioctls to the kernel. It was a ridiculous component that HTC added that basically allowed you to copy files as the kernel. I have no idea why you'd want to do that. It did a whole bunch of other things as well. Another example of why sockets can be bad. The list goes on and on. The photo binder socket was also used incorrectly on LG devices to root them. The init run it, I think, was on Samsung. And like I said, the list goes on and on. There's a really great presentation called Practical Android Exploitation. If you just Google that string, you'll get a presentation that goes through a lot of these in more detail. Some of the things I've done personally that are not listed on here, in my experience, I've used sockets several times to root my own devices. This is either using surprisingly, TCP sockets listening on Android devices, as well as Unix sockets. And I have some examples from a high level that I can share in the next few slides. Okay, so if we wanted to use a socket, we could use a variety of different programming languages. I'm not going to talk about the modules for each of these, but they're there, and you can do it from pretty much anywhere you'd like. It doesn't matter what language you're using, it's always going to lead to a system call. So the system calls are what we care about. They're included in this particular library if you actually cared. And let's talk about a few of them in a little bit of detail. We'll talk about the server side first, and we'll talk about the client, and then how to communicate data. I'm not going to put up examples up here with the arguments and stuff. I'm just going to talk a little bit about what they're used for. If you're a server and you want to listen on a socket, the first call you need to make is the socket system call. This is going to return a file descriptor, because on Linux, everything is a file, right? This is going to return a file descriptor, but it takes 3 key arguments. The reason I have these listed is because these are very important in determining what type of socket you're going to use. The domain, the type, and the protocol. I'm going to talk about each of those in the next few slides, so I'm not going to talk about them now. Next, once you've created your file descriptor, you're then going to bind this file descriptor to something. And something really depends on what type and family of sockets you're using. For example, if you're using a iNet socket, you're going to bind it to a port and IP address. But if you're using a Unix socket, you're not going to bind it to that, you're going to bind it to a file name. So basically you're binding something to a file object. Next, you're going to listen for connections. You're going to tell the operating system that you want to listen to connections on this particular file descriptor by calling the listen function. Finally, on the server side, you're going to call the accept system call, and this is a blocking system call, which will halt execution until someone actually connects to you. From here, you're going to return your own client file descriptor, which can then be used to exchange data. Okay. On the client side, it looks very similar to start, but it doesn't follow through like the server side. We start off by calling socket, providing the same types of arguments. Again, the domain, type, and protocol. Also the bind call, which I said maps the file descriptor to something. And then in this case, we call connect. And in some instances, you don't actually have to call connect. I'll go through examples of that. But we're basically then telling it that on this file descriptor, I want to actually reach out and connect to this other file descriptor, which could be across the network, on the same system, somewhere else. To actually send data between them, there's a variety of different system calls you'd use here, depending on the family and the protocol that you're going to use. What's kind of interesting is, well, I find this interesting, that you can actually call read and write on sockets. Because everything is a file, you can read and write files on Linux. You can also call read and write on socket objects. I don't know why you would. You'd probably use something like send or send message, which actually handles some more of the encapsulation better for you. Okay. So let's talk about the domains. This is the first argument to the socket call and tells basically we'll call it the genre of sockets you want to use. I have 3 listed here. There's a whole bunch of them maintained by the kernel in this file if you, for some reason, like reading kernel source. But there's a whole bunch more that you could use. These are the 3, I guess you could count 4 by calling AF iNet 6.1. These are the 3 that I see the most frequently on Android devices. And we're going to go through each of them in a couple slides. The types. This is the second field in that first socket call. And if we're going to call the domain the genre, this is kind of like the subgenre or the characteristics of that particular genre. Again, maintained by the kernel in some file that nobody probably cares about, but they're there. These are interchangeable depending on what domain you want to use. Sock stream, this is basically equivalent to TCP. This is reliable connection. This is a sequential, so everything gets reordered for you. But it doesn't really mean TCP. It's just a way to describe the connection. We also have sock dgram, which is basically UDP. We don't have any of that ordering and connection stuff that we have for sock stream. And then there's plenty more. I'm not going to talk too much about sec packet, but it's kind of similar to stream, but it has fixed lengths. And then there's socket raw, which you're kind of on your own, doesn't write any header information for you. If you've ever used a tool like Nmap, they're probably going to use raw sockets. They're very quick. You can write your own headers. You can build things much faster in C than if you actually used the stream and packets. Again, like I said, there's plenty more that I'm kind of glossing over. Okay, so I have this little example here in Python. Hopefully you guys can see it in the back. I'm going to walk through some really basic examples for using clients. In Python, it's very easy. It's maybe 6 or 7 lines. In C, it's probably 30 to 40, and I couldn't fit it on the slide, so Python it is. So AF iNet and AF iNet 6. When somebody says create a socket on this web server, I can almost bet 99% of the time they're talking about these sockets. This is what we see most frequently on the internet. These are designed to traverse networks. Right, so there's a whole bunch of capabilities built into the protocol to actually allow you to move packets across the network. The key takeaways here are the types that it accepts and also the bind arguments. So in this case, bind is going to look for an IP address and a port. Oops, sorry. I already kind of mentioned that, but when we want to bind something here, unfortunately in Python there is no bind. It's just combined with connect here. I'm giving it an IP address and a port, and then I'm using that send function to send a message to it. In this case, the types that we most frequently... Question?
You wouldn't need to find it good enough to connect. The bind is only if you want to set sending port.
Okay. That's a fun little fun fact there. Is that in Python or is that in C as well? Okay, cool. So some of the types that you're going to see most frequently here are sock stream as well as sock dgram. This is basically equivalent to TCP and UDP. For AF Unix, does anyone ever work with Unix sockets? Okay, we got in the front. All right. Unix sockets, also shortened as UDS, these are what we'll see commonly between processes on a Linux system. If I have one process that needed to talk to another one, there's a variety of different ways you could do it. The domain sockets are just one of them. There's no networking capabilities built into Unix sockets, so you wouldn't be able to use it to go across the network, which means that these sockets are much more lightweight than the AF INET counterparts. In this case, the bind call we'll talk about actually accepts a file name of the socket type or an abstract name, and I'll talk about what those are in a second. Abstract names are always going to start with a null byte, so keep that in mind if you're seeing some program and you see that weird, this little guy here. That's an abstract Unix socket. The types here are similar to INET. We're also going to see sock stream, sock dgram, and you can use sock sec packet if you'd like as well. All right, just two quick examples here, very similar. Unfortunately, this one's cut off a little bit on this side, but they're pretty much the same thing. Notice I have AF Unix and sock stream when I'm creating my socket. This one over here, I'm actually giving it a file, so dev socket silly. And this one, I just have that null byte and then a string. So they're both valid if these sockets existed, and this is how you could send messages to them in Python. Okay. All right, the last one is the AF netlink socket that I'm going to talk about. So netlink sockets are probably the most complicated of these that I have up here. They're historically used to do networking between the kernel and user space, but it doesn't have to be that way. You could add your own netlink family and create your own protocol around that and use that on a device or a system in general. Primarily, like I said, used to talk from the kernel to someplace in user space. This is that vol-d vulnerability I was talking about on Android where a user space process needed to hear messages from the kernel, and that's how they was able to push those messages through using netlink sockets. The bind call here accepts the process ID and the netlink group. So the netlink group is sort of kind of like the type of netlink socket you want to use. In this case, I've added my own, but other times you'll see like netlink underscore firewall, netlink underscore route, netlink underscore something. These are all maintained in that kernel file here. This example is really contrived because with netlink sockets, you usually have to build your own header, and you have to follow the specifications to that particular family here, or group. So this one, I think it'll kind of reconstruct it in Python for you, but you'd probably have to do a little more research on your own to actually figure out how to use this particular socket. Okay, so now that we know what sockets are, we can kind of talk about how we can start looking at these on Android devices. So Android is built off Linux, so we can use all of the IPC mechanisms that are provided by Linux. We can use pipes, we can use ioctls, we could use system calls, shared memory, all those things still apply on Android, but we could also use sockets. And I see a lot of sockets used on Android. Ioctls are obviously very important as well. Android does have shared memory that's called ashmem on Android, but I do see a lot of sockets that are used improperly. So I'm just going to be focusing on them. If you're writing an application on Android, you're probably not going to use any of those. In fact, you're probably going to use the binder class in conjunction with intents to send messages that way. It's so much easier to use in Java as well as C, and I would say 99% of the time, any app you download off the Play Store is going to use that framework. It doesn't have to be, though, especially a lot of applications that come on Android devices that are designed to be background processes as part of the OS. Those ones might be using these sockets that I'm describing. Okay, so let's talk about non-applications, those other use cases I was describing. So for AF Unix sockets, as I mentioned, these have been used historically to root many devices. They're mostly for application to native daemon communications. So native daemons are usually C programs running on Android. There's quite a few of them if you look in the dev socket directory. Those are all the Unix sockets that are probably native daemons, but they could be mounted anywhere, really. Any socket file could be your Unix, your native daemons. What was I going to say about those? The one that I know particularly that's kind of interesting is the netd daemon. This is the daemon that handles doing routing updates for you on your device. That listens on dev socket netd. And it's restricted on who can access it by the Linux file permissions, so you can't just connect to that and start sending crazy messages. But there's been a bunch of vulnerabilities on as part of Android where you could do command injection and stuff through that, since it is basically executing routing commands for you. For AF netlink sockets, these are mostly, like I said, from native daemons to the kernel. Usually you don't see an Android application using netlink sockets, but I guess there's no reason why you couldn't have a native component of your Java application to actually communicate with the kernel if you even have the privileges to. And like I said, the example is that vol-d process from before. The last one I said is the AF inet sockets. And to be quite fair, I don't really know why you'd want to use these. It doesn't really make much sense to me as to why you'd want to have a TCP or UDP socket listening on your phone. I can't imagine why, but it still happens. And I'll talk about a few examples in a little bit, but I just don't think there's really a reason for using these. I think developers should be shunned for using those. Right, but why?
The thing I've used before is for relaying messages from the local network over SMS.
So you would run a web server on your phone, and then
You send a message to that web server on a local LAN IP address.
isn't that like kind of dangerous though? Like, what if you were like in a coffee shop with that running?
Sure.
I guess that's the point. Like, I could see like that example, but you could also use USB and tunnel over that, right?
Yeah.
So I guess there are reasons, but I just don't think it's a good practice unless you're doing some other sort of security on top of it. But like I said, it still happens, and it still happens improperly. So what if you want to start looking for sockets? So if you're on a Linux system, or in our case, Android, the sockets are going to be found and maintained in the procnet directory. So there's file listings in there that you can actually cat. And this will give you information about the sockets that are connected or listening or whatever state they're in. If you cat that file, probably not going to have a format that's really good for you to look at. This is an example of catting, I think, the TCP file. Just the headings don't line up. They're not actually what they look like here. It's kind of a frustrating format. So the netstat binary is what the operating system uses to actually parse these out. It makes it much easier for you to understand. But on Android, because it's not meant to be like an administrative system, the netstat binary that you have is pretty stripped down. It's part of the toolbox binary, which is a stripped down version of BSides, which is already stripped down. So you really don't get the control that you really want when it comes to parsing these files. So we have a couple options. One, you could compile your own netstat if you wanted to, but then you have to make it work for whatever device you wanted to, so I'm just going to kind of ignore that as an option. There's nothing stopping you. The better option that I think you should do is to upload the BSides binary. So again, this is stripped down a little bit, but it definitely has more capabilities than the one that's on Android by default. These are already compiled from busybox.net, so you can do a wget to one of those, push it to your phone, and then you can run netstat and get all those nice formatting here for us here. So that's a nice little smiley face there. So the flags that BSides binary supports, the ones that I think are most important are printed here. I'm not going to go through each of them. The ones that I think are the most important are listening ones, extra, and the process ID. These can come in really handy when you're trying to determine who is actually listening on these sockets. Might be a little tough to see in the back, but this is an example for looking for AF inet sockets. So an example command is using the PLE, T, and U arguments. This is going to print all listening TCP and UDP sockets on your device. In this particular example here, these are both relating to the Android debugging bridge. Anyone familiar with that? Android debugging bridge. So, and the last one is just me listening on this port, on port 9999. Depending on your privileges, you may or may not see the PID or the process name. When I ran this one, it was on a rooted device, so that these are here, but if you're using on just your regular device, you're probably not going to see those, which sucks. And we'll talk about how to get around that. This similar command here, instead of using the T and U flags, we can use X for Unix, so PLEX can be used to print the AF Unix sockets. The format here, the things I want to make known are if you have a abstract socket, so I mentioned the abstract one with the null byte at the beginning, it's going to have an @ sign at the beginning here. So there's an application called comjv, and then I think it's local socket, but it's truncated, has a Unix socket called Silly Unix, and we have the Zygote, which is the core process on Android, listening on dev socket Zygote. So if you had the privileges, you could connect to that socket, and that's how Android spawns new processes and forks off your new running applications. So I just want to differentiate the format there, because you're probably like, what's this going on here? Netlink sockets kind of have a sad panda here. The netset doesn't parse these out for you, so you have to parse that file yourself. The format is kind of documented. There's some things you can look for online. Otherwise, you're going to be digging through the kernel source and various parsers of it to determine what each flag is, because the fields in there aren't very helpful. I don't know if I have a screenshot in here, but it's a little more tedious. But you can get the information you need to determine who's listening by actually parsing that file out. Okay, so now we know how to find the sockets. Now, how do we connect to the sockets? And I provided a bunch of different methods here that you can use. Some of them are better for different types of sockets. The first method is we can use ADB forwarding. So as I kind of mentioned or hinted at, ADB is the Android debugging bridge, which allows you to connect to your phone with physical access. So if you're doing developing or whatever and you want to connect to your phone, you could use the Android debugging bridge. One really cool feature it allows is you can actually forward connections from your local system to the device, which is kind of what I was talking about the gentleman in front. You could forward connections from my computer to my USB connected phone. I use this because if I want to write a client for some socket that I find, I don't want to have to use it on the phone, and I'll explain why. I'd rather write it locally in Python or something really easy that I could write it and then just forward it to the phone. It supports TCP and both types of Unix sockets, so yay for that. It doesn't support Netlink, unfortunately, so we'll have to do different options there. You could use whatever you want. This is that Telnet example here. So a couple slides ago, there was this guy on, where is it? 99999, or sorry, 4 nines. So I just connected to that using Telnet, and lo and behold, it's a Telnet server. Cool. But it could be anything. It could return command prompt or something. It's just now we're able to connect to that socket. But notice I'm giving it my local IP address, the local host, and the port, and I set up the forwarding there. So that's the quickest, I think, to do this. You can set up the forward rule really easy and then connect. The second method is to compile and upload SOCAT. Does anyone ever use SOCAT? SOCAT. It's kind of like NetStat. I'm sorry, NetStat. Netcat. So it provides the ability to connect to sockets and even listen on sockets. It's really flexible. It does TCP, UDP, Unix, and a whole bunch of other things. If you want to use it, it's already pre-compiled here, but just a warning, it's not mine. So you're on your own if you want to download that. I've used it, so I'm either compromised or not. So that's your second option. This is maybe a little bit slower than the last one, but it works the same. It has its advantages. The third one is to create a Java application. These classes do exist for you to use. You could use the local socket and local socket address classes if you wanted to deal with Unix sockets, which is what this image is here. This is me just connecting to that silly Unix socket and sending a message. Pretty straightforward. There is the native daemon connector class that's not public. That doesn't mean you can't use it. It just means that you need to know how to use it and import some classes into the IDE so it actually will stop yelling at you. And that's this over here. So if you see this here, creating an object with a callback, the name of your Unix socket, and some other information here, that would be if you wanted to use the native daemon connector. If you want to just use iNet sockets, just like when we're across the network, you use the socket class. One thing to note here, again, there's no null byte here, which is a little confusing. That is going to be an abstract Unix socket. There's a flag used to say if you want to actually be a file in that constructor. So you have to look at the documentation, make sure you're using that right. And this right here, this is not abstract. This is actually a file, and it will automatically point you to this directory. So when you try to use that native daemon connector on netd, it's going to open up dev socket netd. And again, no support for netlinks here. The last option is going to be the slowest. There's no example here, but you could always write a C or C++ program. There's a bunch of advantages here. It works on every socket as long as you have the right cross-compiler. You could write your tool, upload it. It supports AF Netlink, which the other ones didn't. This is going to be, when it comes time to actually write your exploit or your proof of concept to actually connect to these sockets, sometimes the Python or the Java ones just aren't going to cut it for what you need to do, especially when you're dealing with Netlink. But yeah, that's kind of outside the scope of this. Okay, so now we know how to find sockets, we know about the different types of sockets, and we know how to connect to sockets. Now we can actually start looking at some of the ways we can attack these different sockets. So real quick, I'm just going to plug some tools that I created here. I'm not going to spend too much time talking about these, but I will reference them in here. If anyone's interested in some of this work and likes testing their devices, I recommend checking out my device testing framework. It's in 2 different Git repos here. The framework itself and then all the content. It's not a vulnerability scanner, it's more of a, I guess we'll call it an exploration framework. It automates a lot of cool tasks like collecting data and processing it. It'll process all applications to a database that you can query, which is really useful for just understanding what's on your phone. And it also has modules that help you understand potential security risks. For example, when permissions are used improperly or missing permissions and stuff like that. Again, if anyone has any questions about that afterwards, just see me after I can help you out. So, we have the tools we need, but we got to figure out who is listening. So there's 3 basic areas where we're going to find people listening. The first is Java applications. And I said that they're probably not going to be using these sockets, but you'd be surprised. Sockets can be used, and for example, the gentleman on the front said you're running a web server. There's nothing stopping you from doing that. It has its advantages and disadvantages, but that could be done. So we're going to see most likely iNet sockets as well as Unix sockets. The Unix sockets we're probably going to see for applications that are probably part of the operating system, and less so than apps you'd pull from the Play Store. With native binaries, I'm just going to call them daemons here. You could see all 3 of them, to be honest. I've seen all 3 of them used. Each one of them has its own vulnerabilities that are associated with it. So we have the most work to do there. Finally, the kernel, probably less likely to see iNet or Unix. Probably most likely going to see the AF netlink sockets there. So that, like I said, netlink is the most difficult one, in my opinion, to deal with, the hardest to test. So that's the only one we're really going to see in the kernel. So an AF iNet example. This screenshot here shows me running it on a device I was testing. It doesn't always happen, but look at this guy here, 1668. I wasn't sure what that was. This is a real screenshot from some testing I was doing. Whenever I see anything in this list, I kind of mark it up and I'm like, all right, this needs more research because, again, I'm not sure why you'd want to do this. This is just a stock device, no apps that I've created, just bought from the store, plugged in, and this thing is just listening here. So I want to look into this. So determining who is listening can be a little bit of a challenge if we don't have root. If we have root, that PID field is going to be populated for us, and we can see exactly who it is. If it's a binary, if it's an application, we can reverse it and figure out what's going on. If it's not, though, we got to kind of dig around and figure it out. And because at the end of the day, when we're connecting this to a socket, the port number is just going to be a number. So I can't look for the number 1668. I guess you could, but it's not the best way to do it. So there's other things we could do. If we're looking in applications, particularly Java applications, we can look for uses of the server socket class. So you could acquire all the applications off your phone, unpack them all using something like Boxsomali or APK tool, and then you could grep across all the code for any instances of the server socket class. Or you could use some modules from my testing framework called dex search, which does essentially that, where I can search for the string java-net-server socket and see that I have 2 hits here with their names obfuscated. And then I can look into those applications to see exactly where that class is being used. From here, it's just a simple reversing technique where we're looking through it and figuring out if there's some sort of protocol, what the format it's accepting, etc. If we have a binary or a native daemon, the process is a little more tricky. We can't just grep for that string because it might just be calling the socket function. But we can use that to our advantage. If we go back to that screenshot I have where the socket's definitely listening on our phone, one way you could do this is you could do first a process listing. Show me all the process listing on the device, then pull all the binaries off the phone. This regex here could be used to do something very similar to that. And then for all of those binaries that are both on the phone and running, look for the dynamic symbols socket bind listen accept. So you can use anyone use NM before? It can dump symbols and a whole bunch more of binaries. Look for those 4 symbols actually existing, and that should be a good indication that this binary is using sockets. Now, there's shortfalls here. It could be obfuscated. It could be encrypted. Yeah, you're kind of on your own for that case. But this is a quick way that we can determine which binaries have the capabilities to create a server socket. From there, we'd have to reverse the binary, again, outside of the scope of this talk, but you could use something like IDA Pro or R2. So here's my quick little script here that I wrote for this. It's a one-liner, but it's actually 4 lines. But really all it's doing is what I just described there. And you can see these guys are all running, but they also have those 4 libraries, or those 4 symbols. And this one down here is kind of weird. Store intent translate.x. I thought that was kind of strange. The other ones I see a lot on phones, so DHCPD, okay. G-sensor calibrate, okay. Those sound like things you'd see on a phone. But this last one to me is just kind of bizarre. So with that in mind, the next thing that I would do, since I have no idea who's listening here, I'd probably just try to talk to the socket and see what happens. One thing you should always do is you should always look at the Android logs. So you can use the ADB logcat command to show you what's being printed into the logs. And developers are so nice about putting things in the logs that help us understand what's happening. These are either there because they forgot to be removed, or they're there for reasons they wanted them to be there. But it's really useful to do this. In this particular example, you can see here we found the socket 1669. Then I set up my forwarding rules, and then I'm just using netcat to send a string ASDF to that port. Notice how it kills my session immediately. But then in the logs, we see this error message from, oh, look at this, store intent translate, that says error, only support get, ASDF, ASDF. Okay, cool. So now I know it's this process, and I cheated here a little bit. You could have to be a little more creative with your grepping. But now we know that it's definitely this process. We definitely want to reverse that binary, and we want to see what's going on here. And just a spoiler alert, this binary would basically accept commands and execute them as root. So using this socket on this particular device, you could effectively root the phone, which I think is pretty fun. What's really interesting about this was the developers, I don't know what they were thinking, they used this binary, which is running as root, to execute a command to launch not the Play Store, but their own version of the Play Store. But I have no idea why you'd want to do it this way, because you already can do that using intents. They were using the command line to generate an intent to send it, and it just, to me, it's kind of interesting. Anyway, you could use, in this case, an iNet socket to actually root this particular phone. So that was fun. Okay, how about an AF Unix example? So these are really, really easy to search for because we have a string. So abstract ones are even easier than file-based ones. File-based ones might have a little more noise, but abstract ones are really cool and easy to search for. Here's me just running netstat again with the PLEX, grepping for just the abstract ones. And here's a whole bunch of them here. This is on my Sharp phone, which, anyone know Sharp made phones? Yeah, maybe a couple people. They make phones, so they make one in the US, and I bought it to see what was going on. So what I need to do at this point is ask myself, which one of these are part of the OEM package, or which ones are actually part of the Android open source? I've done this enough to realize that all of these guys here are actually added by Sharp. So each one of these is something I want to look into. One of these up here, I'm not going to say which one of them, was used to be able to basically mine the location of a device by connecting to it and issuing a special command, which Sharp then fixed pretty quickly because there was no permissions at all. You just opened a socket here and then requested the location through it every second or whatever, and you could follow a user around. Kind of fun. But in our case, it's definitely not the factory settings service one, which also to me is kind of interesting. And if anyone wants to look into this, it's kind of exciting. But this one, because we have that string, we can again do that grep method I was talking about. We can grep across all applications for factory settings service as a string. In this case, there's only one example, and it's not in an application, it's in a framework, the jp.co.sharp.android.factory settings. And then we can grep again and figure out it's in this exact file here that string occurs. And if you open up that ipc.somali file, it's all the commands that are supported by that socket. So now we can start testing that. If you're doing native binaries, you can do the same script I mentioned before. These slides will be available if anyone wants to try them. But just in this case, it has those 4 functions, so socket bind, listen, accept, and also has the string factory settings service. To be honest, you could probably just grep for factory settings service across every binary. There's probably only going to be a few hits. It's probably not a very common string. Okay, so if you wanted to connect to these, again, you could use any of those 4 methods. The one that I chose to use here is using socat on the phone. You could use some different fuzzing techniques here to see what happens. In this case, all I'm doing is sending a bunch of A's, trying to be a hacker here. But what we see in the logs is factory setting service, receive action 97, right? 97 is the ASCII for that, for one of those at least. So we know that the first byte is something to do with some sort of command, and then it's like, yeah, that's an unknown command, so I'm not running that. But what's kind of cool is if you look at this IPC file, it has all the accepted commands in there. And some of them are like clear settings and do this. And notice there was no permissions anywhere here. This is just a socket listening that we can connect to and send these commands, and it's called factory setting service. So, I don't know. I think it's kind of fun. Okay, so netlinks, I don't have any really cool exploits or things that I found for these, so I just have some slides to kind of give you some information. As I mentioned earlier, these are definitely the most difficult to trace and replicate. You probably could have a whole presentation on netlink sockets, but there's really good information on the internet. If you just look up netlink socket PDF, there's I think one by Red Hat that's pretty solid. By parsing out that netlink file in the procnet directory, the two pieces of information that we can attain are the netlink group and also the PID. So here's a little script here as part of my framework that does just that, since netstack doesn't do it for me. Again, I asked myself which ones are part of the AOSP and which ones are OEM added. There's two on here. There's actually several more. There's one up here like Google Apps.magazine. Not sure why it's listening on a netlink socket, but it is. Also, there's binary added that's called audit-D, and COM Samsung Android MTP application. This is off a Galaxy Note 3. So these are some ones that I might want to look at first because they've been added and they might be added incorrectly. The first step, what you'd have to do is you were able to get the group from before, but you have to determine what that group actually means to that phone. Because these are maintained by the kernel, different phones have different kernels, and these groups relatively stay the same, but they don't have to stay the same. So if we look at the kernel source for my Note 3, group 9 for audit-D, lo and behold, oh, it's kind of hard to see. Group 9 corresponds to netlink_audit. So we would now have to look up the netlink audit protocol, determine how that's used, and it may be possible to send messages to whoever this process ID is here, I'm not sure. That could cause him to crash or do something, I don't know. But that's an area we could look at. The same thing is true for this application here. Like, what is group 15 and how is it used? Is it on here? 15 U event messages. So I think you could, that was the one that was used by Vol-D. So I don't know if there's actually a specific reason to use U event other than just sending events to user space. But it's something to definitely look into to see if there's a problem there. If you want to look for areas in the kernel where netlink sockets are created, you can do some quick greps, which is obviously not the most effective way, for the function netlink_kernel_create. This is what you're going to see in the kernel to actually generate netlink sockets. This is from the BlackBerry Priv. Anyone know BlackBerry is making Android phones? It's a really badass phone. So this is the kernel source from the BlackBerry Priv, which is a Qualcomm-based phone. So we see this function, QSEECOM. This is some sort of Qualcomm driver that has been added. We see the netlink kernel create calls for a family that I'm not familiar with, netlink_QSEECOM. And there's been a whole bunch of vulnerabilities that have come out on this particular protocol family. This is something you'd have to actually look into, again, like I said, to see if there's any vulnerabilities here. But you could kind of trace through what happens outside of this init function here in the kernel and see, how is it actually grabbing the data? What's it doing with it? How can we abuse this? Do you have a question? No? Okay. Okay. The last little slide I have here is in user space. For netlink sockets, you're not going to be using the connect or, the listen or accept. So just looking for binaries with socket and bind, or even just socket but not listen and accept might be a way for you to determine the netlink sockets here. What's also interesting is you can use that file here, the procnet netlink, which is going to have the PID. So from here, you can just run a PS and figure out the actual process. And to be honest, you can just look here. So system bin audit-D. This is just a screenshot illustrating that from the Vol-D. So you can see us setting up the netlink header here, calling socket, setting some socket options, and then calling bind. And then directly below here, it's just like send message or receive message. And that's where the vulnerability was where it basically just ran this routine and then waited for connections and then did something based on that. So that's all the examples I have for each of the 3 sockets. So I just want to have a quick little conclusions here for you guys. If you take away anything from this talk, it's probably these things that I didn't have any cool like 0 days or demo or anything, but sockets are definitely an important component of Android platform security. If you're going to look at sockets on Android, I would focus most of my effort on these particular sockets. I showed you guys the tools you can use to both find the sockets as well as interact with them, depending on what type of socket it is. I didn't talk too much about how to fuzz these things. So you could have full talks on how to fuzz things, but those are some of the things you would do from there. If you have a rooted phone, it actually makes this whole process a lot easier. You can use debuggers, tracers, and stuff like that. But a lot of this stuff can be done without a rooted phone. All these phones all these screenshots were taken from non-rooted phones, except a couple that I used the emulator. But like the Note I had, the BlackBerry Priv, my Sharp phone, a bunch of others, those were all not rooted when I did the testing. So you can do all this just with a phone in your pocket right now. And a lot of times these unprotected sockets, they don't do any protections outside of just having the socket there. Now, for Unix ones, you could do a little more fine tuning, and you can actually change the file permissions on the socket itself, since it has an inode entry. Also, on newer phones, they're running SE Android, which has made a lot of this a lot harder. And I purposely didn't talk too much about that, but it just makes it much more difficult to do some things like this. We were able to root a phone a couple months ago by basically we found a socket, we knew it was bad, we knew it had code execution, but the SE Linux policy or SE Android policy did not let us directly communicate with it. So we had to exploit something else and force that to communicate with it, which ultimately led to us rooting the phone. So I just want to say that SE Android has made this much more difficult, but it's still possible and it's still a problem. So with that, I'm going to ask you guys if you have any questions or comments for me.
So I like how you spent a little bit of time sort of mentioning how OEMs are often a problem with Android.
Mm-hmm.
With that in mind, I want to ask you, what kind of phone do you use?
I have a Sharp phone.
And also, can we see it? Because I've never seen a Sharp phone before.
It looks like a child's toy. No, I mean I've played with a ton of different phones, from the newest Galaxies to LG to HTC to BlackBerry. I don't really care. I bought this phone because it was the only one I knew about that I hadn't played it before. I had no idea what Sharp was doing, so I bought it mostly to hack on it, and that's actually worked out for me because everything I found I've reported. So as far as I know, this phone is secure, and XDA developers has not been able to root this phone yet. So that makes me feel a little good. But I would also recommend just the Nexus series. They're, I think, some of the best phones out there. And they routinely get security updates. So between the Nexus and my second pick would be the Priv, the BlackBerry phone. That phone's really cool. So any other questions? All right. Well, it looks like we get to finish up a little bit early here, guys. Thanks for coming and listening to me to ramble about sockets. Hopefully everyone's still awake.